Optimizing for optimistic scenarios. In this chapter, you'll discover that the worst case scenario isn't the only situation worth considering. Being able to consider all scenarios is an important skill that can help you choose the appropriate algorithm for every situation. Insertion sort. One of the sorting algorithm that will reveal the power of analyzing scenarios beyond the worst case is insertion sort. Insertion sort consists of the following steps. First, in the first pass-through, we temporarily remove the value at index 1, the second cell, and store it in a temporary variable. This will leave a gap at that index since it contains no value, like this. So the 4 has been moved up to a temporary variable. In subsequent pass-through, we remove the values at the subsequent indexes. We then, so in subsequent pass-throughs, we remove the values at the subsequent indexes. So we remove here in the second pass-through. We then begin a shifting phase where we take each value to the left of the graph and compare it to the value in the temporary variable. So we compare this 8 and in this temporary. If the value to the left of the gap is greater than the temporary variable, we shift that value to the right. As we shift values to the right, inherently the gap moves leftward. As soon as we encounter a value that is lower than the temporarily removed value, or we reach the left end of the array, this shifting phase is over. We then insert the temporarily removed value into the current gap. Then fourth, step 1 to 3 represents a single pass-through. So that's the single pass-through. Next, we move the index here to 2, and then we move this up 2, and then compare it to this left value as well. As we move in each pass-through, we repeat these pass-throughs until the pass-through begins at the final index of the array. By then, the array will have been fully sorted. So these are the sorting algorithm that is the best, one of the best way to explain the optimistic scenarios. So the benefits of the optimistic scenario when we're optimizing our app for that scenario. Now let's see that in action. Let's apply the sort insertion sort to this array 42713. Now we know that the sorted value for this is 12347. We begin the first pass-through by inspecting the value at index 1. This happens to contain the value 2. Step 1, we temporarily remove the 2 and keep it inside a variable called temp underscore value. We represent this value by shifting it above the rest of the array. Step 2, we compare the 4 to the temp underscore value, which is 2. Because 4 is greater than 2, we shift the 4 to the right. There's nothing left to shift as the gap is now at the left end of the array. Step 4, we insert the temp underscore value into the gap, completing our first pass-through. Next, we begin the second pass-through. Step 5, in our second pass-through, we temporarily remove the value at index 2, which is 7. We'll store this in temp underscore value. In this case, the temp underscore value is 7. We compare the 4 to the temp underscore value. The 4 is lower, so we won't shift it. Since we reach a value that is less than the temp underscore value, this shifting phase is over. So we move to the third pass-through. Step 7, we insert the temp underscore value back in the gap, ending the second pass-through. We now begin the third pass-through. So in the third pass-through, we begin the step 8. We temporarily remove the 1 and store it in temp underscore value. Step 9, we compare the 7 to the temp underscore value. Step 10, the 7 is greater than 1, so we shift the 7 to the right. So this is a compare step and this is a shift. So as you have noticed, each step we either compare or we shift. Step 11, we compare the 4 to the temp underscore value. The 4 is greater than 1, so we shift it as well. So the 4 is greater than 1, so we shift that to the right. And then we compare the 2 to the 10th value. So that's another step. Comparison step. Step 14, the 2 is greater, so we shift it as well. Now the gap has been reached the left end of the array, so we insert the temp underscore value into the gap, conducting this pass-through. Now we begin the fourth pass-through, since we're done with the putting the temp underscore value on its left empty index. Step 16, we temporarily remove the value from index 4. This is the unique step that we've done in this sorting, in which aside from compare and swap, we temporarily remove from index 4, making our temp underscore value, this is the value 3. We compare the 7 to the temp value, so here 3 and 7. The 7 is greater, so we shift the 7 to the right. We compare the 4 to the temp underscore value, and then step 20, the 4 is greater than 3, so we shift the 4. We compare 2 to the temp underscore value. As you can see here, instead of before 1, we compare it in no other than empty cell. Here, there's still another number we could compare, but as we will later see, the 2 is later less than 3, so our shifting phase is complete. And then step 22, insertion. We insert the temp underscore value back into the cup. So here is another unique step, which is the insertion step. So our array is now fully sorted. So as we have mostly comparison and swap step, and then the first removal is kind of like deletion, and then after that insertion, which is kind of like shifting. Insertion, again, in the previous chapter or videos we discussed that inside insertion there's actually a shifting step. So here's a Python implementation for that insertion sort. Sorry, I just took coffee. So we define insertion under sort and then a parameter array. For index in range 1, length array, temp underscore value is equals to array index. So we the value of this index, we put that in a temporary value. Now position is equals to index minus 1, because this index we were gonna compare that to the left. While position is greater than or equals to 0, so we start with 0, of course. We loop it. If array position is greater than temp underscore value, if that position is greater than temp underscore value that we put here, then an array, we add 1 to the right. So we change the value of position to the right because it's greater than temp value. So again, we remove or we delete temporarily the index 1. Therefore, and then we compare that to the left, and then if it's greater, we put that to the right. So that's this code is about. Now position is equals to position minus 1, else break. Array position plus 1 is equals to temp underscore value, and then we return array. So let's explain this line by line. First, we start a loop beginning at index 1 that runs through the entire array. So this is how we begin on the index 1 that runs onto the entire array. Or we start with a for loop. So each round this loop, so we missed that, right? Because we thought that we were only using while loop, or at least I thought. Each round of this loop represents a pass-through. So each round for this for loop represents a pass-through. Within each pass-through, we save the value we're removing in a variable called temp underscore value. So in this pass-through, since we started with 1, we store that temp, we save the value we're removing. So we delete and then we save that on temp underscore value equals to array index. Next, we create a variable called position, which will start immediately to the left of the index of temp underscore value. This position will represent each value we compare against the temp underscore value in this for loop. Now, as we move through the pass-through, this position will keep moving leftward. So these are the inner loop as we compare each value to the temp underscore value. We then begin an inner while loop which runs as long as position is greater or equal to 0. So we started with 1 and then an inner loop that will serve that pointer that will compare the left to that temporary value. We then perform our comparison, that is, we check whether the value at position is greater than the temp underscore value. So this is actually the comparison step that our computer used to determine the comparison on each value on the cell. So these are, in terms of time complexity, are the steps within the loops. So if this is how you write this code, if array position, so the array to the left or the position is greater than the temp underscore value that we save and we deleted. So if it is, we shift that left value to the right. So like what I've said earlier, array position plus 1 is equals to new value array position. We then decrement position by 1 to compare the next left value against the temp underscore value. Now we decrement the position so that in this last phase in which we compare the 4 and then the 2, so we compare this 4 first and then we decrement the position 1 to compare the 2. Now if it's greater, we put that to the right as well. So if at any point we encounter a value at position that is greater or equal to the temp underscore value, we can get ready to end our pass-through, since it's time to move the temp underscore value into the gap. So if at any point we encounter the value at position that is greater or equal to the temp underscore value, we put that to the right. Now if it's not greater than value, we then create a line of code that will handle that. Therefore, if we break that, those missing or empty temporary value will automatically jump into that empty cell. Now the final step of each pass-through is moving the temp underscore value into the gap. So we break the loop and then we actually created a code. So array position plus 1, which represent the position to the left plus 1 is equals to temporary underscore value. Now we save the temporary underscore value to that position plus 1. After that's how we move it to the gap, because that empty cell will always be position plus 1, position to the left plus 1, because we're moving it it's either we're moving it to the right and then we move the 1 in the left. So we decrement the array or the position by 1. Therefore, the position plus 1 besides it or on the right of it will always be the empty cell. So after all pass-through have been completed, we return the sorted array. Now what's the efficiency of insertion sort? Like what I've said, the efficiency of this sorting algorithm is in its best case. Now 4 types of steps occur in insertion sort: removals, or like deletions, comparisons, shifts, and insertions. A comparison take place each time we compare a value to the left of the gap with the temp underscore value. In worst case scenario, each value to the left of temp underscore value will always be greater than temp underscore value. So worst case scenario, those left value or left index will always be greater. Therefore, we have to shift and more than we would have to if it's not greater, right? So the pass-through will only end when the gap reaches the left end of the array. So the pass-through will only end if the empty cell is on the left of the array, because therefore we are able to sort it from lowest to highest during the first pass-through, in which temp underscore value is the value at index 1. A maximum of one comparison is made since there is only one value to the left of the temp underscore value. So the first pass-through will always have one comparison because we start with the index 1 and compare it to index 0. On the second pass-through, a maximum of two comparisons are made because we start with index 2 and we compare it to 1 and 0 and so on. On the final pass-through, we need to compare the temp underscore value with every single value in the array besides temp underscore value itself. So we need to compare it in the final pass-through with every single value in the array besides the temp underscore value itself or the index itself. In other words, if there are n elements in the array, a maximum of n minus 1 comparisons are made in the final pass-through. When examining this pattern, it emerges that for an array containing n elements, there are approximately n squared over 2 comparison. So this pattern showed that the steps for comparing this type of sorting algorithm are n squared over 2. So it's still high because we have this two loops, two nested loops. Shifts occurs each time we move a value one cell to the right. So when we move that, if it's greater, the position is greater than the temp value, we move that to the right. When an array is sorted in reverse order, there will be as many shifts as there are comparisons, since every comparison will force us to shift a value to the right. So let's add this up. N squared over 2 plus n squared over 2 is equals to n squared steps. Removing and inserting the temp underscore value from the array happens once per pass through, since we move that back the temporary value. And since there are always n minus 1 pass-throughs, we can conclude that there are n minus 1 removals and n minus 1 insertions. So since there are always n minus 1, the number of step minus 1 pass-throughs, we can conclude that there are n minus 1 removals and n minus 1 insertions. So these removals kind of like not gonna matter because those comparison and shifts are n squared already. So here we can simplify it to O n squared plus n, but there's a catch. Let's see. N squared comparisons and shifts combined, n minus 1 removals plus n minus 1 insertions. So that's n squared plus 2n minus 2 step. It emerged that in a worst case scenario, insertion sort has the same complexity as bubble sort and selection sort. They are all O n squared. I noted in the previous chapter that although bubble sort and selection sort are both O n squared, selection sort is faster because selection sort has n squared over 2 steps compared with bubble sort's n squared steps. At first glance, then we'd say that insertion sort is as slow as bubble sort since it's take n squared plus 2n steps. But actually it's not that simple since there's an average and best case scenario. Now here's the average case. Take a randomly sorted array, for example. What are the odds that the values will occur in perfect ascending or descending order? It, it's much more likely that the values will be over the place. Now, we discussed in the previous videos the bell curve. So what happens most of the time is the average scenario. We're just measuring the speed of the algorithms based on worst case scenario. So we could be prepared and sure that those will happen even with the worst case scenario. Now in the best case scenario, where the data is already sorted in ascending order, we end up making just one comparison per pass through and not a single shift, since each value is already in its correct place. So since we remove that index 1, in best case scenario, when we remove that index 1 and then store it in temporary value, we just need to compare it to the position, and that's the best case scenario. So it's an O1 step. So in the worst case scenario, we compare and shift all the data, and in the best case scenario, we shift none of the data. So worst case, we shift all, and in the best case, we shift none, and just make one comparison per pass through. For the average scenario, we can say that in aggregate, we probably compare and shift about half the data. Thus, if insertion sort takes n squared steps for the worst case scenario, we'd say that it takes about n squared over 2 steps for the average scenario. In terms of big O, however, both scenarios are O(n) squared. In worst case scenario, or in worst case, 4, 3, 2, 1, there are 6 comparisons and 6 shifts for a total of 12 steps. In an average case of 1, 3, 4, 2, there are 4 comparisons and 2 shifts for a total of 6 steps. So again, 12 and then 6, because n squared over 2 and n squared. In the best case, 1, 2, 3, 4, there are 3 comparisons and 0 shifts. So contrast this with selection sort. Selection sort takes n squared over 2 steps in all cases. So here, from worst to average to best case scenarios. This is because selection sort doesn't have any mechanism for ending a pass-through early at any point. So this is the difference with insertion and selection. The insertion has a mechanism for ending it a pass-through early at any point, because it's just how the algorithm are designed. So as you can see, for best case, we only have n step for insertion sort. For average case, n squared over 2, and for worst case, it's n squared. So each pass-through compares every value to the right of the chosen index no matter what in selection sort. So it's kinda inefficient for a best case scenario. So if you have a reason to assume you'll be dealing with data that is mostly sorted, insertion sort will be a better choice. If you have a reason to assume you'll be dealing with data that is mostly sorted in reverse order, selection sort will be faster. If you have no idea what the data will be like, that's essentially an average case, and both will be equal. So that's how you choose what sorting algorithm you would use. Now, a practical example. Suppose you are writing a JavaScript application, and somewhere in your code, you find that you need to get the intersection between two arrays. The intersection is a list of all the values that occur in both of the arrays. Here's one possible implementation. Function, so intersection, first array and then second array. Let result is equals to is empty array. So we create this empty array for. So we have for loop here. Let I equals to 0, and then if I is we start with 0. If I is less than the array, that length, we increment, and then we have this inner for loop, which starts with j equals to 0, and then if j is less than second array, that length we increment. So if first array I is equals to second array j, therefore we met an intersection, and then we result that push to first array I, and then we return the results. So here we are running nested loops. In the outer loop, we iterate over each value in the first array. So we iterate in each value in this array. So the computer moves to all of the index on that first array. As we point to each value in the first array, we then run an inner loop. So as we point each, we then run an inner loop. So it's doing it simultaneously. That check each value of the second array to see if it can find a match with the value being pointed to in the first array. So imagine like the computer, while it's pointing it, there's another loop that check if it's match on that second array. So kind of like this comparison made in each step of the point of the first array. Now there are two types of step taking place in this algorithm: comparisons and insertions. We compare every value of the two arrays against each other, and we insert matching values into the array that result. So result that first array I. Now, if the two arrays are of equal size, and say that n is the size of either array, the number of comparisons performed are n squared. This is because we compare each element of the first array to each element of the second array. Thus, if we have two arrays that each contain 5 elements, we'd end up making 25 comparison. So this intersection algorithm has an efficiency of O(n) squared. The intersection at most would take n steps. The insertions at most would take n steps because the insertion you would do is the number of the array that you have as well. So you cannot have or insert just more than the elements of the array or less than it if the two arrays happen to be identical. Now this is a lower order compared to n squared. So we'd still consider the algorithm to be O(n) squared because we in categorizing big O, we don't care about these constants. So we only care about the we care about the highest degree of order, such as n squared. If the arrays are different sizes, say n and m, we'd say that the efficiency of this function is O n times n. Now in the current implementation of the intersection function, we make n squared comparison in all scenarios, no matter whether the arrays are identical or the arrays do not share a single common value. However, so in this two arrays, whether they have identical array or identical value in each index of the array, or the arrays do not share a common value, we still iterate on those two arrays n squared because we need to run two loops in each index to point on those each index. However, where the two arrays share common values, we really shouldn't have to check every value of the second array against a value of the first array. So if the two arrays have a common values, or we already know that it's identical, we shouldn't have to check every value of the second array against that value of the first array. Let's see why. So here, it's a necessary step, this 5 and then comparing it to here, because we already know that the only identical value here is the 8. So in this example, as soon as we find a common value, the 8, there's really no reason to complete the second loop. We're performing an unnecessary step. So to fix this, we can add a single word to our implementation. So here, with the addition of break in this, we didn't need to iterate another loop for the for loop for the its parent loop. Let j equals to 0, since we can end that since we already know that there's no other identical values left, kind of like removing the steps needed, breaking it for insertion that allows for early break compared to selection sort, which needs to compare all the values even though it already have this stored value initially. Now with this addition of the break, we can cut the inner loop short and save steps and therefore time. Remember, while it's good to be prepared for the worst case scenario, average case are what happens most of the time. Now that we've covered the important concepts related to big O notation, let's apply our knowledge to practical algorithms. Now, big O in everyday code. Additionally, once we know how our code is categorized in terms of big O notation, we can make a judgment call as to whether it may need optimization in the first place. For example, an algorithm that's O(n) squared is generally considered to be a slow algorithm. So if we have determined that our algorithm falls into such a category, we should take a pause and wonder if there are ways to optimize it. Of course, O(n) squared may be the best we can do for a given problem. However, knowing that our algorithm is considered slow can signal to us to dig deeper and analyze whether faster alternatives are available. So the first step of solving a problem is recognizing that there is a problem, or the first step of improving something is measuring what where we currently at our speed, right? So mean, average, or of even numbers. The following Ruby method accepts an array of numbers and returns the mean average of all its even numbers. How would we express its efficiency in terms of big O? So here, we define average of underscore even underscore numbers, and we accept an array. So how would we express its efficiency in big O? Here, the code is like this. First, the mean average of even numbers will be defined as the sum of the even numbers divided by the count of even numbers. So we keep track of both the sum and the count. So sum equals to initially 0.0, count of underscore even underscore numbers initially equals 0. Now we iterate through each number in the array, and if we encounter that even number, we modify the sum and the count. So array that each do this, it accept a number as parameter. If number that even, question, sum plus equals to number. Then count of even numbers, increment plus or equal 1. And then end and end. And we return the mean average. Return sum over count underscore of underscore even underscore number. So here, what we did is that the even numbers divided, we keep track of the even numbers, which is to the sum. So sum is equals the value of the even numbers. We put that on the sum and then we add that. So here, sum is plus equals to number. So the number that has even value, if number that even, we add that using the sum variable. Now remember that big O is all about answering the key question. If there are n data elements, how many steps will algorithm take? Therefore, the first thing we want to do is determine what the n data elements are. In this case, the algorithm is processing the array of numbers passed into this method. This then would be the n data elements, with n being size of the array. So here, we actually have one type of data, which is numbers, and we determined that this array would be the n here, or the data we put into here, is the n data elements on that array parameter, with n being the size of the array. Next, we have to determine how many steps the algorithm takes to process these n values. So we need to determine the steps that this loop takes. So again, as you can see, we start with n, and then the next thing is the steps that the loops process. So we can see that the guts of the algorithm is the loop that iterates over each number inside the array. So the gotcha is again the loop. So we'll want to analyze that first. Since the loop iterates over each of the n elements, we know that the algorithm takes at least n steps. So at least in a worst case scenario, there is n steps we've done in this array. Looking inside the loop, though, we can see that a varying number of steps occur within each round of the loop. For each and every number, we check whether the number is even. So we compare it. Then if the number is even, we perform two more steps. We modify the sum variable. So we add that, the even that we compare. So we insert, and we modify the count underscore of even numbers variable. So that's another insertion. So we execute 3 more steps for even numbers than we do for odd numbers. As you learned, Big O focuses primarily on worst case scenarios. In our case, the worst case is when all the numbers are even, in which case we perform 3 steps during each round of the loop. So inside the loop, we perform 3 steps: comparison, insertion, to both count and then the sum. Because of this, we can say that for n data elements, our algorithm takes 3 n steps, 2 insertions and 1 comparison. That is, for each of the n numbers, our algorithm executes 3 steps. Now our method performs a few other steps outside of the loop as well. Before the loop, we initialize the 2 variable and set them to 0. So that's another steps. Technically, these are 2 steps. After the loop, we perform another step, the division of sum. So before and after the loop, there's actually another steps. So we initiate a variable, and after that, there's a division of the sum over count numbers. Technically, so those are, what's that? That's an operation as well. Technically, then our algorithm takes 3 extra steps in addition to the 3n steps. So the total number of steps is 3n plus 3. So 3 is constant because it only happens before and after the loop. So it will only multiply by the 3 if it's inside the loop. However, you also learned that Big O notation ignores constant numbers. So instead of calling our algorithm O times 3n plus 3, we simply call it ON. Word builder. The next example is an algorithm that collects every combination of 2 character strings built from an array of single characters. For example, given the array A, B, C, D, we'd return a new array containing the following string combinations. Following is a JavaScript implementation of this algorithm. Let's see if we can figure out its Big O efficiency. Function, word builder, we accept an array. Let collection equals to an empty array. So that's a first step. For let I, so we iterate in this array less than the length. And then we have another loop for let j equals to 0, j is less than array dot length. So if I is not equals to j, collection dot push array I plus array j. So if it's not the same, we push that as a first one combination, and then we loop onto the entire array. So it's kind of like the same as well as the insertion algorithm, in which it points to the array, and then another loop inside this array are comparing each the value. So here we're running one loop inside another. The outer loop iterates over each other in the array, keeping track of the index j. So the outer loop iterate over each character in the array on the array that you put. So keeping track of the index I. For each index I, we run an inner loop that iterates again over each character in the same array using the index j. So after that iteration and then keeping track of it in I, there is another loop, kind of like in the nested loop, in the inner loop that iterates again over each character in the same array using index j. Within this inner loop, we concatenate the characters at I and j. So within that inner loop, if we see a different combination, we push that or we concatenate that combination, with the exception of when I and j are pointing to the same index. So to determine the efficiency of our algorithm, we once again need to determine what the n data elements are. In our case, as in the previous example, n is the number of items inside the array passed to the function. Again, n is the data elements. The next step is to determine the number of steps our algorithm takes relative to the n data elements. So again, we need to determine the steps that our algorithm took with that n data elements. That's why it's data structures and algorithm, because with that n data steps or data that you put on the algorithm, how many steps that your algorithm takes to process that to complete its task, kind of like the task we've discussed in about face, in which the consumer used to achieve their goal. Now in our case, the outer loop iterates over all n elements, and for each element, the inner loop iterates again over all n elements. So which amounts to n steps multiplied by n steps, kind of like insertion. Again, this is the classic case of O(n) squared, and it's often what nested loop algorithm turns out to be. Now that would happen, what would happen if we modified our algorithm to compute each combination of three character strings? Of course, it would be n times n times n, which is n cubed. That is, for example, array of a, b, c, d. Our function would return this array. Here's an implementation that uses the nested loops. What is its time complexity? So here we have I, j, and then k. And then if I is not equals to j, not equals to or not pointing on the same as j, and j is not pointing as the same as k, and I is not pointing as k, we push that array I plus array j plus array k. Then we return the collections, which is the name of our array. So again, there is another step there aside from n cubed, which is the variable, but that's constant. Technically, it's n cubed plus 1. But again, in big O, we disregard that. Now, in this algorithm, for n elements, we have n steps for the I loop multiplied by the n steps of the j loop multiplied by the n steps of the k loop. So this is n times n times n, which is n cube steps. So again, in each loop, we multiply all of those because all of those has n step, because those loop needs to iterate on each array. So iteration could be it's on n steps. It could be there's a comparison made, something like that. But that's the classic measurement for nested loops. N times n times n, which is n cubed, which described as O n cubed. Array sample. Array sample takes a small sample of a large array. We expect to have a large array, so our sample is just the first, middlemost, and last value from the array. So it's just a small sample of that large sample array. Here's a Python implementation of this function. So we define a sample array, and then first we create the first var array is equals to array 0, middle is equals to array integer length of the array divided by 2 if it's middle, and then the last is array minus 1. So we determine this is actually just the index, the first, middle, and last. So return first, middle, and then the last index. So in this case, the array passed into this function is the primary data. So we can say that n is the number of elements in this array. However, our functions ends up taking the same number of steps no matter what n is. reading from the beginning, midpoint, and last indexes of an array. Each takes one step, no matter the size of the array. So, in the actually in this nested loops that we've done, we're reading each of the data elements and then we're comparing it. So it's kind of like n steps, right? It could be more steps, but it's not an n squared. So the big O doesn't really disregard those comparison steps. But here we push it. Technically, it's another steps. But the main thing here is that this type of loop is an n cube steps. So here it's the same as well. In this case, the array passed into this function is the primary data, so we can say that it's the n. However, our functions ends up taking the same number of steps no matter what n is, because we're just reading the first, middlemost, and then the last index. Reading from the beginning, midpoint, and last indexes of an array each takes one step no matter the size of the array. Similarly, finding the array's length, dividing it by 2 also takes one step. So these are using the computer's or memory's internal ability to read. So this type of function is fast. So since the number of steps is constant, that is, it remains the same no matter what n is, this algorithm is considered O1. So as we saw, this loop are reading in the first loop of I, and then it's reading the first loop of J, then reading the it in K. So if we're only reading in I, that only takes n step. Because we need to iterate on each index of the array. Here, the reason why it's O1 is because we don't need to iterate in each of the index of the array. So that's kind of like a thing to remember, which is going back to the basics, in which our computer are reading it fast if it's if doesn't need to iterate on all of the index. So here, average Celsius reading. Let's say we're building a weather forecasting software to determine the temperature of a city. We take temperature readings from across many thermometers across the city, and we calculate the mean average of those temperatures. So we'll calculate the temperature in a various location, different location in a city, and we calculate the mean of that. We'd also like to display the temperature in both Fahrenheit and Celsius, but our readings are initially only provided to us in Fahrenheit. So the initial reading is Fahrenheit, so we need to convert that as a step as well. So to get average Celsius temperature, our algorithms does two things. First, it converts all the readings from Fahrenheit to Celsius. Then it calculates the mean average of all the Celsius numbers. So first it converts all from Fahrenheit to Celsius, then it calculates the mean average of all the Celsius numbers. Following is some Ruby code that accomplishes this. We define an average underscore Celsius Fahrenheit underscore readings. So we define this average underscore Celsius function and accept a Fahrenheit readings. Now Celsius underscore number, we create an initial empty array, and then so collect that will serve as our a way to collect Celsius numbers here. Now we convert it each reading to Celsius and add to array. So how do we convert that and add to array? Fahrenheit underscore readings that each do to the Fahrenheit reading, Celsius dash underscore conversion equals to Fahrenheit dash reading minus 32 over 1.8. Celsius underscore numbers dot push. So we push it on Celsius underscore numbers in this empty array, the Celsius underscore conversions, and then end. And then getting the sum of all Celsius numbers. So we start with sum equals to 0.0. Celsius underscore numbers each do Celsius underscore numbers sum plus equals, so each of the value put here on 0.0 would be added, and then it will be equals to Celsius underscore number. So each of the we do sum for each of the Celsius underscore number that we put on the array, and then end, and then we return the sum over Celsius underscore number that length for us to get the mean. First, we can say that n is the number of Fahrenheit underscore reading passed into our method. So again, n is the number of Fahrenheit reading passed to the method. Inside the method, we run two loops. The first converts the reading to Celsius. So it's not a nested loop. The second sums all the Celsius numbers. So we have loops, each do loop. That's the name of the loop. Since we have two loops that each iterate over all n elements, we have n plus n, which is 2n, plus a few constant steps, which is initializing the variable, the array, as well as the initializing this sum, and then returning. So those are technically 3 steps, but we ignore that because it's just one step. Don't get thrown off by the fact that in the earlier word builder example, 2 loops leads to an efficiency of O(n) squared. There, the 2 loops were nested, which has led to n steps multiplied by n steps. In our case, however, we simply have 2 loops, one after the other. Clothing labels. Let's say our code accepts an array of newly produced clothing label items stored as strings and creates for every possible label we'll need. Specifically, our labels should contain the item name plus its size ranging from 1 to 5. For example, if we have the array purple shirt, green shirt, we want to produce the label text for those shirt, like purple shirt size 1, purple shirt size 2, and then green shirt until 5. So here's the Python code that will create this text for an entire array of clothing items. So again, we starts with the array or the output or the end in mind of what we will gonna produce, and then before we create the code. So here's the Python code. We define a function mark underscore inventory, and we accept clothing underscore items, and then we initiate an array clothing underscore option equals to open and close bracket, and then we create a for loop for item in clothing underscore items. So for sizes 1 through 5, Python ranges go up to second number but do not include 8. So for sizes 1 through 5, we create another for loop for size in range 1, clothing underscore options that append item plus the size plus string of size. So here's the size 1 to 6. So the Python ranges up to the second number, which is the 6, but it doesn't actually include the 6. So it's only gonna read 1 to 5. So clothing underscore options that append. So in Python we append it. So here's the clothing underscore options array we create, and then we append the item that we insert on that array, or the user input on our mark underscore inventory function, plus the size. But on those size, we only iterate 1 to 6, it's like constant, plus the string size, and then return clothing underscore options array. Now, the clothing items are the primary data being processed. So n is the number of clothing underscore items. So that's the n again. But in this case, however, outer loop runs n times. Our inner loop runs a constant of 5 times because it only runs from the sizes 1 or range 1 to 6. That is, the inner loop will always run 5 times no matter what n is. So while our outer loop runs n times, so it's still a nested loop, the inner loop runs 5 times for each of the n strings. Well, this means our algorithms runs 5 times. This is reduced to O(n). Since big O notation, ignore constants. So we have n times and then 5 constant step, which technically, since an inner loop, we need to multiply it, so it's 5n steps. So since we need to ignore, it's just an O(n) time complexity. Now count the ones. This function accepts an array of arrays where the inner array contains ones and zeros. The function then returns how many ones there are. So for this example input, our function will return 7 since there are 7 ones. So we're counting the ones here. This function accepts an array of arrays. So it accepts a nested arrays as a parameter. So again, we start with the output before we create the function. Then the function will return how many ones there are on that array of arrays. So for this example input, our function will return 7 since there are 7 ones in this nested or multiple arrays or nested arrays, since these are one array with 3 arrays inside it. Now here's the function in Python. We define count underscore ones function and then we accept an outer underscore array. Count is initially equals to 0 because that's there's no 1, we start with the index 0. For inner underscore array in outer underscore array, so we count the inner underscore array in that outer underscore array, and then we have another loop for number in inner underscore array. If number is equals to 1, we add a count to 1, so we increment that count to 1 if we found a 1. So it's kind of like, since it started with 0, we add 1, and then when we find 1 on that inner array, we add again, and then we return the count. So that's how we calculate it. Again, it's easy to notice that the nested loops and jump to the conclusion that it's O(n) squared. However, the two loops are iterating over two completely different things. The outer loop is iterating over the inner arrays, and the inner loop is iterating over the actual numbers. At the end of the day, our inner loop only runs for as many numbers as they are in total. Because of this, we can say that n represents how many numbers there are, and since our algorithm simply process each number, the function's time complexity is O(n). So it's not actually n squared, even though we have two nested loops here. Now why is that? Because the outer loop is iterating over the inner arrays. Now the inner loop, though, is iterating over the actual numbers. So here is the inner loop for number in inner array. So we're just doing comparison whether it's 1, 2, or 0. At the end of the day, our inner loop runs for as many numbers as there are in total. So it's constant because the number total here is only 1 and 0. So we're just comparing that. It's not really O(n) squared because the inner loop does not depend on the n that we put, because the numbers that we put is either 1 or 0. So kind of like in sizes in clothing, in which the size that we have in inner loop are constant no matter what, how many indexes that outer loop iterates. So palindrome checker. A palindrome checker is a word or phrase that reads the same both forward and backward. Some examples include race car, kayak, and divide. Here's a JavaScript functions that determines whether a string is palindrome. So function is palindrome, and then again our parameters is string. Now start the left index at index underscore 0. Let left index equals to 0, and then let right index equals to string dot length minus 1. So we start with the first index with the left index, and then the last index with the right index. While so iterate until left index reaches the middle of the array. So while left index is less than string dot length over 2, if the character on the left doesn't equal the character on the right, the string is not a palindrome. So if string left index is not equal to string right index. So that's the only way for us to know if it's palindrome. If the left of the middle and right of the middle is equal, then return false, it's not palindrome. Then move left index 1 to the right. Left index plus move right index to the left, right index. So if we got through the entire loop without finding any mismatches, the string must be palindrome. So here, after in this while loop, we also have left index pointing on all the index to the left. So we iterate it, move right index 1 to the left. Actually, we move the left index 1 to the right. So the left index starts with 0, we move that up to the right, and then right index move from the last index to the left until it gets to the middle. Now if we got through the entire loop of this without finding any mismatches, the string must be palindrome, and we return true. In this case, the n is the size of the string passed to this function. The guts of the algorithm takes place within while loop. Now this loop is somewhat interesting because it only runs until it reaches the midpoint of the string. So this loop will not run all of the index in the array. That would mean that the loop runs n over 2 steps. So this is the time complexity. Get all the products. Our example is an algorithm that accepts an array of numbers and returns the product of every combination of numbers. For example, if you pass in the array 1, 2, 3, 4, 5, the function returns 2, 3, 4, 5, 6, 8, 10, 12, 15, 20. This is because we first multiply 1 by 2, 3, 4, and 5. Then we multiply by the 2 by 3 and 4 and 5. Next, we multiply the 3 by the 4 and the 5. And finally, we multiply the 4 by the 5. Note something interesting. We multiply, say, the 2 by the other numbers. We only have to multiply it by the numbers that are to the right of it. We don't have to go back and multiply 2 by the 1, because that was already covered back when we multiplied by the 1 by the 2. So each number only needs to be multiplied by the remaining numbers to the right of it. Here's a JavaScript example of this algorithm. Function, two number products array. So two number products is the name of the function, and we accept array. Initially, we create an empty array products, outer array. So we created a for loop, I equals to 0, and then we increment on all of the array. And then in inner array, in which j always begins one index. So as you can see, here is the implementation in JavaScript. For JavaScript, we create an array using let keyword. So here in the for loop, we also use let to initiate on that first index of the array. Now in inner array, in which j always begins one index to the right of I, so we create a for loop again, and then let j equals to I plus 1, and then closing semicolon, and then if j is less than array dot length. So as you can see, guys, we use the array here, length, but in other input in JavaScript we have string, but we still so we use that input string dot length as our parameters in while loop, for loop, etc. So here outer underscore array, for inner underscore array, in outer underscore array. Let's see another example of incrementing in for loop. So here for is a Python for item in clothing underscore items. So this is how we do the for loop in Python. For item, we don't have a let. There's some for loop that needs a left as well. Let me just check that. Here, so array, since that's the input, so notice that whatever input in our functions as a parameter, we use that to measure the length here in the for loop. So that's how JavaScript works. So here first that array length, and then if let j is equals to 0, so for JavaScript this is how we create it. And then for array, open and close bracket. And then we push in a array using first the name of the array variable that we created, and then here first array I, which is the result of our loops. So there you go, guys. So I just want to express that on how we actually create that for loop in the background. So where are we? So here's the JavaScript implementation of this, getting all the products. So function two numbers products, we have an array. So we have an outer array for loop I equals to 0, I is less than array length, and then inner array in which j always begin one index to the right of I. So since this multiplication only calculate anything to the right of it, so j is equals to I plus 1. So we're moving additional plus 1 once we calculate that product. So j is less than array length, and then products that push equals to array I times array j, and then double close, since it's the first close, and then this is the closing parenthesis. So here return products and then close. So n is the number of items in the array passed to this function. We run the outer loop n times. We actually run it n minus 1 times, but we'll drop that constant. The inner loop though is different, since j always begin one index to the right of it. So again, n is the number of items in the array passed to this function. We run the outer loop n times. We actually run it n minus 1 times because we start with the first index. Now, but we'll drop that constant. The inner loop though is different. Since j always begin one index to the right of j, the inner loop number of steps decreases each time that it's launched by the outer loop. So each time it's launched by the outer loop, the index number or length is decreasing by 1. When j is 0, the inner loop runs while j is 1, 2, 3, and 4. Because it doesn't need to run the 0, only 1, 2, 3, and 4. When j is 1, the inner loop runs while j is 2, 3, and 4. When j is 2, the inner loop runs while j is 3 and 4. When j is 3, the inner loop runs while j is 4. When all is said and done, the inner loop runs 4 plus 3 plus 2 plus 1 times. To put this in terms of n, we can say that the inner loop runs approximately n plus n minus 1 plus n minus 2 plus n minus 3 plus 1 times. So this formula always turns out to compute to about n squared over 2. We can visualize this in the diagram on. For the purpose of the diagram, we'll say that n is 8. So there are 82 or 64, 8 squared or 64 squared. So here's the graph. If you work your way from the top row to the bottom, you'll see that the top row has all n squares shaded gray. The next row has n minus 1 squares shaded gray, and the one after that has n minus 2 gray square. This pattern continues until the bottom row, which has just one shaded square. This demonstrates that the pattern of n plus n minus 1 plus n minus 2 plus n minus 3 plus 1 is equivalent to n squared over 2, which again, in big O categories, will drop the 1/2 and will make it n squared. Again, this is an example of an inner loop. We figured out then that the inner loop runs for n squared over 2, but because big O ignore constants, we express this as O(n squared). So for getting all the products, that's always going to be n squared over 2 or n squared. Now, dealing with multiple data sets, now what happens if instead of computing the product of every two numbers from a single array, we instead compute the product of every number from one array by every number of a second array. For example, if we had the array 1, 2, 3 and the array 10, 100, 1000, we'd compute the product as 10, 100, 1000, 20, 200, 2000, 30, 300, 3000. Our code would be similar to the previous snippet with some slight modifications. So here, we have a function named toNumbers products, array1 and array2. Let products equals to an empty array. So what is this? It's a JavaScript as well. For let I equals to 0 and then I array1 that length iterate. So we have two arrays parameter here. So in inner for loop, for let equals j equals 0, j less than array2 that length, semicolon j plus plus, products that push array I times array2 j, and then return products. So here, instead of calculating all the products of the numbers with only one combination of that, as in moving to the right of it, as in the previous example, here we actually have to multiply each, kind of like in here, 10, 100, 1000, and 1, 2, 3. First, we multiply it by 10, and then 100, and then 1000. Then 2, multiply it by 10, 100, 1000. So we multiply each of the index in the array. So here it's going to have a different n. It may not be the n squared over n that we have since we're only moving to the right. First, what is n? This is the first hurdle, as we now have two data sets, namely the two arrays. It's tempting to lump everything together and say that n is the total number of items of both arrays combined. We don't want to consider n to be the total numbers of integers from both arrays, since we'd never be able to pin down the efficiency in terms of big O notation, as it varies based on different scenarios. We're in a bit of a bind here. We have no choice but to express the time complexity as O(n) times n, where n is the size of one array and m is the size of the other. This is a new concept. Whenever we have two distinct datasets that have to interact with each other through multiplication, we have to identify both sources separately when we describe the efficiency in terms of big O. While this is the correct way of expressing this algorithm in terms of big O notation, it's a little less useful than other expressions of big O. Comparing an O(n) times n algorithm to algorithms that only have n and not an m is a little like comparing apples to oranges. However, we do know that there's a specific range in which O(n) times n lies. That is, if n and m are the same, it's equivalent to O(n) squared. And if they're not the same, and we arbitrarily assign the smaller numbers to be m, even if m is as low as 1, we'd end up with O(n). In a sense then, O(n) times n can be construed as a range between O(n) and O(n) squared. So the time complexity is between O(n) or n and n squared. So password cracker. Let's say you decide on a brute force approach and write some code that produces every possible string of a given length. Here's the code you whip up. So you define every password n, and then so you create this function, every underscore password, and then you have an input n, and then a. Inside that you have a string a times n, and then up to string z times n. Each do string, and then puts so you multiply that
from A to Z to the n, and then puts the string n. So the way that this works is you pass in a number to the function, which becomes the variable n. If n is 3, for example, the code A times n produces the string AAN. AAN. AAA. The code then sets a loop between all possible strings within range of AAA and ZZZ. Running this code will print AAA. So if n is 4, like when printing every 3 character combination, we end up with 26 times 26 times 26 combination. So length 1, only 26 combination. Length 2, 26 squared. Length 3, 26 cubed, etc. If we look at this in terms of n, it emerges that if n is length of each string, the number of combination is 26n. Therefore, in big O notation, we express this as 26n. This is an utterly glacial algorithm. So 26n is not actually n steps, okay? It's an exponent of 26. So depending on the characters that we have, we raise that to that number of characters, such as if 3, 26 raised to 3. The truth is that even an algorithm that this is a mere O 2n is incredibly slow. So 2 raised to n is actually already slow. Let's see how it looks on a graph compared to some of other algorithms we've seen so far. So 26 raised to n is actually the slowest. In a certain sense, O2 raised to n is the opposite of O log n. With an algorithm of O log n like binary search, each time data is doubled, the algorithm takes one additional step. With an algorithm of O2 raised to n, each time we add one element of data, the algorithm doubles in steps. In our password cracker, each time we increase n by 1, the number of steps get multiplied by 26. This takes an incredible amount of time, which is why brute force is such an inefficient way to crack a password. Armed with this knowledge, you'll be able to methodologically optimize your code for speed. In the next chapter, we'll discover a new data structure that is one of the most useful and common tools for speeding up algorithms. So we will gonna discuss the hash table now. So let's begin. I'll just speak just a moment. Alright, so let's begin. Mhm. So blazing fast lookup with hash tables. Imagine you're writing a program that allow customers to order fast food from a restaurant, and you're implementing a menu of foods with their respective prices. You could technically use an array like this. So it's an array within an array menu, French fries, and then 0.75, etc. So this array contains several sub arrays, and each sub array contains two elements. The first element is a string representing the food on the menu, and the second element represents the price of the food. As you learned in why algorithms matter, if this array were unordered, searching for the price of a given food would take O(n) step, since from the computer would have to perform a linear search. So if it's unordered, we'll have no choice but to make a linear search operation as a search function. But if it's unordered, we can use a binary search. If it's an ordered array, the computer could do a binary search which would take O log n. However, we're gonna now introduce a new data structure which is blazingly fast. It's like an O(n) fast, so hash table. So most programming language includes a data structure called a hash table, and it has an amazing superpower. Fast reading. Note that hash tables are called by different names in various programming language. Other names include hashes, maps, hash maps, dictionaries, and associative arrays. Here's an example of the menu as implemented with the hash table using Ruby. So menu equals to, it's just a one open and closing semi bracket. I don't know what it's called, but French fries string is equals and then greater than arrow to 0.75 and then comma, etc. So a hash table is a list of paired values. The first item in each pair is called the key, and the second item is called the value. In hash table, the key and value have some significant association with one another. In this example, the string French fries is the key and 0.75 is the value. In Ruby, you can look up a key's value using the syntax menu and then French fries. Notice we look it up using a key. Looking up a value in a hash, not the value, right? So looking up a value in a hash table has an efficiency of 0.1 on average, or O(1) rather, as it usually takes just one step. Hashing with hash functions. So let's see. Hashing with hash functions is the process of taking characters and converting them to numbers in a known as hashing. So hashing in a hash function is the process, it's actually a process of taking characters and converting them. And the code that is used to convert those letters into particular numbers is called a hash function. So the code is actually the hash function, and that process of converting inside that code is called hashing. There are many other hash functions beside this one. Another example of hash function may be to take each letter's corresponding number and return the sum of all the numbers. So aside from conversion, we could also return the sum of those numbers. If we did that, BAD would become the number 7 following a two-step process. First, BAD converts to 214 because letter B is equivalent to number 2 and A is equivalent to 1. We then take each of these digits and get their sum. 2 plus 1 plus 4 equals to 7. Another example of a hash function may be to return the product of the letters corresponding numbers. So in this case, we're gonna return the multiplication in each of the numbers. This would convert the word bad into the number 8. First, bad converts to 214. Step 2, we then take the product of these digits. 2 times 1 times 4 equals to 8. As you can notice, this turns into two-step, a constant 2 steps. Instead, in the getting all the products example, which would take this as n squared, right? So real-world hash functions are more complex than these, but this multiplication hash function will keep our examples clear and simple. The truth is that a hash function needs to meet only one criterion to be valid. Hash functions must convert the same string to the same number every single time it's applied. So that's the only characteristics or attributes that it needs to be true, is that every time it converts it, which is the process of hashing, to the right value, therefore it's a hash function. If the hash function can return inconsistent results for a given string, it's not valid. Example of invalid hash function include functions that use random numbers or the current time as part of their calculation. With this function, bad might convert to 12 one time and 106 another time. Note that this hash function dub will also convert into 8, just as bad will. This will actually cause some issues that I'll address later. So building a thesaurus for fun and profit, but mainly profit. So our thesaurus works like this. When a user looks up a word in Quick Thesaurus, it returns just one synonym instead of every possible synonym, as old-fashioned thesaurus apps do. Since every word has an associated synonym, this is a great use case for a hash table. After all, a hash table is a list of paired items. We can represent our thesaurus using a hash table. Thesaurus equals to open and close semi-square bracket. Under the hood, a hash table stores its data in a bunch of cells in a row, similar to an array. Each cell has a corresponding number. So under the hood, hash table also store it in a cell in the memory like an array. Each cell has a corresponding number, for example 1, 2, 3, 4, 5. So we ignore the 0 because anything we multiply to that will always be 0. Since we're dealing with multiplication hash function. So like hash function can be more complicated, or is often more complicated, but this is a good start. Let's add our first entry into the hash table. Thesaurus bad equals to evil. In code, our hash table now looks like this. Bad is equals to greater than, pointing to evil. Let's explore how the hash table stores this data. First, the computer applies the hash function to the key. Again, we'll be using the multiplication hash function described previously. So this would compute as bad equals to 2 times 1 times 4 equals to 8. Since our key bad hashes into 8, the computer places the value evil into cell 8. Now let's add another key value pair. Thesaurus cub equals to taxi. Again, the computer hashes the key cub equal 3 times 1 times 2 times 6. 3 times 1 times 2 equals to 6. Since the resulting value is 6, the computer stores the value taxi inside the cell 6. Let's add one more key value pair. Thesaurus ace equals to star. So notice it's just a string, and we have a quotation inside of entering it in this hash function. To sum up what's happening here, for every key value pair, each value is stored at the index of the key after the key has been hashed, which is the process of converting it number. Now ace hashes into 15, since ace equals to 1 times 3 times 5 equals to 15. So star gets placed into cell 15. So in our code, our hash table currently looks like this. Bad is to evil, cub is to taxi, ace is to star. So we determine the indexes of that using the conversion, which is the process of hashing. Now, hash table lookups. Uh, when we look up items from a hash table, we use a key to find its associated value. Suppose we want to look up the value associated with the key bad. In our code, we'd say thesaurus bad. To find the associated value associated with bad, the computer executes two simple steps. First, the computer hashes the key we're looking up. Bad equals to 2 times 1 times 4 equals to 8. Since the result is 8, the computer looks inside cell 8 and return the value stored there. In this case, the string eval. So that's how it is. That's the how it look it up. Now we can now understand why a hash table would yield faster lookup for a restaurant menu than an array. With an array, when we look up the price of a menu item, we would have to search through each cell until we find it. For an unordered array, this would take up to ON, and for an ordered array, this would take up to O log N. Using a hash table, however, we can now use the actual menu items as keys, allowing us to do a hash table lookup of O1, and that's the beauty of a hash table. Hash table is a one-directional lookups because the ability to find any value within the hash table in a single step only works if we know the value key. So that's the that's the key. We need. I mean, that's the yes, that's kind of like the key. We need to know the key in order for us to get the value, but we can't do it the other way around, which is using a value, because it kind of like searching from the computer. Our computer can read it if we know the index. So, but if we want to know the index using the search value, we need to know the location. We need to look because the index is really the location of the data in the memory. If we need to know that using the value, we will have to search all of the value in the memory, which would take ON, right? So if we try to find a particular value without knowing its key, we'd still have to resort to searching each and every key value pair within the hash table, which is ON. This is because the whole premise of the hash table is the key determines the value's location. So the whole premise is that the key kind of like determines the index already. But this premise only works in one direction. We use the key to find the value. The value does not determine the key's location. So we have no way to easily find any key without combing through all of them. While this detail may vary from language to language, some languages store the keys next to the values themselves. So the detail may vary from language to language. Some language store the keys next to the values themselves. So it stores these keys next to the value. This is useful in case of collision, which I'll discuss in the next section. In any case, there's another aspects of the hash table's one-directional nature that's worth noting. Each key can exist only once in the hash table, but there can be multiple instances of a value of that key. If we think about the menu example from the beginning in this chapter, we can have the hamburger listed twice. We can't have the hamburger listed twice, nor would we want to, as it only has one price. However, we could have multiple foods that cost $2.50. In many languages, if we try to store a key value pair where the key already exists, it simply overrides the old value while keeping the same key. So in many languages, when we put a value on that key, it simply overrides the initial value of that key. So dealing with collisions, continuing our thesaurus example, what happens if we want to add the following entry into our thesaurus? Thesaurus dub equals to path. First, the computer would hash the key dub equals to 4 times 1 times 2 equals to 8. Then it would try to add path to our hash table cell 8. Cell 8 is already filled with eval, literally. Trying to add data to a cell that is already filled is known as collision. So trying to add a value to a key that's already filled is called collision. Fortunately, there are ways around it. One classic approach for handling collision is known as separate chaining. When a collision occurs, instead of placing a single value in the cell, it places it uh, in it a reference to an array. So let's look it more carefully at a subsection of our hash tables underlying data storage. Here we have 5, 6, 7, 8, 9, and then 6 has a value string taxi and 8 has a value string eval. In our example, the computer wants to add path to cell 8, but it already contains eval. So it replaces the contents of cell 8 with an array, as shown on page 100 here. So here we add bad. So what it does is that it created an array so that the two could have separate chaining. So what it does is really, instead of placing a single value in the cell, it places in it a reference to an array. So instead of just a single value for that key on the cell or on that location index of them on the memory, it actually make it an array. So remember, we can have two values in one key. So this array contains sub-arrays where the first value is the word and the second value is its synonym. So here the word on that key is the BAD, which convert and the synonym is eval. So that's actually how we build that synonym. Now let's walk through how a hash table lookup works in this case. If we look up Thesaurus DUB, the computer takes the following step. It hashes, again, the process of converting the key DUB 4 times 1 times 2 times 4 times 1 times 2 equals to 8. It looks up cell 8. The computer takes note that cell 8 contains an array of arrays rather than a single value or cell. It searches through the array linearly, looking at 0 of each sub-array. So it looks at linearly, again, that's the first process of linear search, unless it is an ordered array. So it's still the same true in this hash table. It searches through the array linearly, looking at index 0 of each sub-array until it finds our key, DUB. It then returns the value at index 1 of the correct sub-array. Again, it searches through the array linearly, looking at index 0 of each sub-array until it finds our key, DUB. So it finds it in each array inside that cell. So it starts with the index 0, of course, until it finds that DUB. So here 0 and then 1 and then the next would be 2, 3. So it will find that in the 2 cell or 2 index. It then returns the value at index 1 of the correct sub-array. Now let's walk through these steps visually. We hash DUB into 8, so the computer inspects that cell. Here it's all part of the 8, so it has 2 sub-arrays. So since cell 8 contains an array of sub-arrays, we begin a linear search through each sub-array. Starting at the first one, we inspect index 0 of the first sub-array. It does not contain the key we're looking for, which is DUB. So we move on to index 0 of the next sub-array. So we start with the index 0 actually. So we're just finding the key. We actually didn't move with this index 1. So here we found DUB. We found a DUB which would indicate that the value at index 1 of that sub-array path is the value we're looking for. So it starts with the index 0 of each of that cell. So it first convert the 8 to have a fast lookup, and the key in each of the sub-array in that key value 8 will be determined. So using index 0. So it moves to the next index 0 as a process of the linear search. So we found dab, which indicated the value at index 1 of that sub-array path is the value we're looking for, and then we return that. In a scenario where the computer hits upon a cell that references an array, its search can take some extra step as it needs to conduct a linear search within an array of multiple values. If somehow all of our data ended within a single cell of a hash table would be no better than an array. So it actually turns out that the worst case performance for a hash table lookup is ON. Because of this, it is critical that the hash table is designed in such a way that it will have a few collisions and therefore typically perform lookup in O1 time rather than ON time. So we should, even though we could make our way in doing this separate chaining in collision in which we have two values in one key, which is this 8, we need to avoid this. So luckily, most programming languages implement hash tables and handle these details for us. However, by understanding how it all works under the hood, we can appreciate how hash tables eke out O1 performance. So making a hash table, I think we'll have to we'll have to continue with this in the next video. Yep, thank you for watching. See you on the next videos.